Now we're going to talk about limited dependent variables, where a y variable takes a value of just 0 or 1. It can be extended to cases where y takes some limited number of values, maybe 0, 1, 2, 3, but for now we'll stick with the simple case. Y can take a value of just 0 or 1. That could mean that the y variable is going to answer something like a yes-no sort of question. Now, one modeling strategy would be to just use OLS. Ignore the fact that it's going to predict values of y that could be greater than 1 or less than 0. That's actually not a crazy idea. Basic linear model has a lot of strengths, and Mark Bellamy gives a good roundup there in that link. There are other options as well. So often is the case, it's a trade-off. Another modeling method is called logit or probit, which are ways to bend the function so it asymptotes towards 1 as x gets higher, asymptotes towards 0 as x gets lower. It doesn't actually cross those. It's not going to be higher than 1 or lower than 0. It looks basically more like a CDF, cumulative distribution function. The way we set this up, we say there's some probability of y being equal to 1 conditional on a set of x variables. We'll combine those x variables in the usual linear way that we understand. The function, which we'll generically label as f, can have a few bends. So this includes our standard OLS as a special case now. The function is just identity, then we have OLS. But here we're going to twist it around and use a more complicated f function. The logit function looks a little bit complicated. I know it's 1 over parenthesis 1 plus e to the minus z, close parenthesis. Then the probit is going to be phi of z, where phi, that Greek letter there, is the cumulative distribution function of the standard normal. That graph shows the PDF, not the CDF, but we can go between those nowadays. The PDF of the logit and the probit functions. They look very similar. If you squint hard, you might find some differences. The probit is the lighter one in that picture with a little more of the mass in the shoulders, a little bit lower right at the center point. Tails are a bit different, but in most situations, there's not a huge difference. There's some computational complexity. The standard normal is a little more difficult for the computer to compute, so logit functions are used more often. That's perhaps a relic of the old days when computers were slower, or nowadays a statement that you're going to be doing millions of or billions of different calls to that function, and we might care about shaving off a little bit of time. Other machine learning techniques, again, are going to involve even more compute. In assessing how good are the different models, we have, unfortunately, more options. We don't have the simple R-squared measure. Various types of pseudo R-squared have been proposed, but they're not very useful, I think. They push the important questions in the background, which is which miss is worse? Is it worse to predict yes when the true value is no, or is it worse to predict no when the true value is yes? Earlier, we used a terminology of false negative or false positive, type 1 versus type 2 errors. Yeah, statisticians are really exciting people with fascinating names for these things. In general, we might not have a symmetric loss function. We wouldn't think necessarily we're going to penalize false positives and false negatives equally bad. Go back to our little happy face or poopy chart. The rows are whether an observation is predicted equal to 1 or 0. The columns are whether that observation is actually 1 or actually 0. On the main diagonal, we have happy faces. On the diagonal, off the diagonal, we have poop. You have to answer which poop is worse. Which of the bad outcomes is worse? Depending on what you're using the model for, those may be different. If you're modeling, whether it's worthwhile to show an advertisement to somebody online, well, if you've ever been online, you've noticed many of the ads are not for you. But from somebody's perspective, that's not a big loss compared with a possible revenue gain from acquiring a new customer. In other cases, maybe part of the national security apparatus is trying to figure out whether to go arrest somebody. That might have a different loss function. A subsidiary part is to figure out what predicted probability will be interpreted as y equal 1. Often the cutoff is 50%, but depending on the case, depending on the loss function, you might use a different cutoff Experiment, go play around and figure it out. So how do we do this with R? First, I'll note this is the first, not the last, time when you'll see your learning about how to call the LM function transfers right over. R uses the same basic syntax, how to specify a regression function in LM or GLM or many others. That basic y twiddle x comes up in lots and lots of situations. So here, instead of LM, we write GLM, one extra letter. It's a generalized linear model. Then we distinguish logit and probit in the family, where that is either binomial for logit or for a probit, family equals binomial link probit. Yeah, kind of ugly, I admit. Either of these commands will give you a bunch of summary estimates that look incredibly similar to the simple linear regression output. You get coefficients and standard errors and t-stats and p-values, stars and all. Even the interpretation is actually pretty similar. If you want to do t-tests on particular coefficient estimates, see if they're statistically significantly different from 0, then that's the same procedure. And the interpretation, though, is a little more complicated, because the slope is going to be different for different values of the x variables. The function is no longer linear. Whether logit or probit, it's got that bendy shape that I've sketched there. Depending on the value of x, the change in predicted y can be very different. For some people, this is just diminishing returns. If somebody's already got a whole bunch of other x variables that put them in a very high probability of some outcome, then adding a little more isn't going to do much. Going from 96% probability to 97% probability doesn't really move the needle. Whereas a change from 49% to 51%, much bigger difference. As earlier, we discussed about how to interpret linear models with interactions. Often the best way to understand these is to choose some examples, work out the predicted probabilities. You can then calculate how does a little change in the x variable change the calculated probability. In that graph, a point like x1, probability may not change very much. The person has a low probability anyway. But at x2, on the other hand, that point is where the slope is nearly its maximum, so you can see larger changes. It can be difficult to interpret all these coefficient estimates, but as said before, you're at the point where getting results from R is easy. The hard work is to understand and explain what it all means. I'll conclude with a bit of background. At the beginning of your journey, it's okay if you just think this is magic. It works even if you don't know why. But it's useful to begin to get a little bit of sense for what's behind the magic. When we did OLS, we could derive a convenient formula for finding coefficient values to minimize the squared error. Remember, ordinary least squares, the error term is y minus beta x. Sum those up. Having a nice formula makes things easy. But if I didn't know the formula, I could find the same estimates with enough computing power. The computer could just randomly pick values and find the ones that minimize the squared error term. Just pick some number for beta, calculate the error, nudge around the values, see whether errors get better or worse. Similarly, probit or logit is going to find some values of beta that minimize that new error term, which y minus the function of beta x, where that function f is either the logit function or probit. There are other estimators possible. Use a different function there, too, for f. Whatever the function, have the computer find a beta value that minimizes that error. Now, there's a good bit of work being done in the background, people in computer science or mathematics, to figure out what is the most efficient way of doing this search. In the old days when compute was really limited, efficient algorithms are really important. Even in modern cases, computing power goes up, but so too does the amount of data that we're working with, so it's still really important. Now, these problems are pretty much solved for most situations you're going to deal with. What's going on in the background is what's called maximum likelihood estimation, ML. Here's a simple, really simple example. If I see observations from a normal distribution, the likelihood of seeing a particular value is the PDF. I can write that down for 2 observations. For now, keep the math easier, assuming sigma equals 1. So 1 over the square root of 2 pi times e to the minus 1/2 x squared minus mu squared. Deal with that exponent by taking the log. The log function is monotonic, so any value that maximizes the log of a function will also maximize the underlying function itself. Take the log, gives a bunch of constant terms that drop out, minus 1/2 x minus mu squared. Then, as you remember from calculus, whenever you want to find a maximum, you take the derivative, set it equal to 0. Derivative with respect to mu, set that equal to 0. With some algebra, find the best estimate of mu is x1 plus x2 over 2, which, hey, that is exactly the average. Actually, if we go back in statistics history, the normal distribution is sometimes called the Gaussian distribution because a mathematician named Gauss figured out this exact property. With a little more math, you can do the case for n observations and figure a formula similarly if you have to estimate the standard deviation. Maximizing the likelihood of some probit or logit function, more complicated, but people have derived the first and second derivatives, so finding the maximum value is going to be quicker. But that's why when you look at the output, it will sometimes tell you something about how many steps it took. Sometimes it might be a very long time, or it might not converge. There are various ways to try to solve that problem, twiddling convergence criteria, giving more time. Its default is to sort of give up after a few times. Sometimes you just have to tell it to run longer. But, all things down the road, you will be working yourself through.